Okay, so what we're going to do today is review for test two. There were a couple topics we weren't able to cover on the Saturday review session. Those came up with these four topics here: current density, resistivity, resistance of a wire, and RC circuit. So we'll just go ahead and go through these in this order here. Okay, so to start, we're looking at current density. Just a quick reminder what current density is. So current density, we use the symbol J, and we usually write the current density as I over A, where I is current and A is the cross section of a wire. We typically don't do any problems that are more difficult than that. We tend to look at the current density in a wire only, although we could get a little bit more general if we wanted to. In addition to I over A, we can always write that the current density, J, is due to some number of charge carriers, okay? And charge carriers are usually electrons, but by convention, we look at the flow of positive charge when we use our equations. And so we'll use positive E here for the charge of the charge carriers. We use the letter N for the density of charge carriers in the wire. And then we use the speed of those charge carriers times the cross-sectional area A. And this, or excuse me, no A here, this is the current density. So essentially it's the number of charges that are available to freely move in the system of the wire times the charge of those actual charge carriers times their velocity. And it's a specific kind of velocity called the drift velocity. And this drift velocity here is very small compared to the random motion. So small compared to the random motion of the charges. Okay, and we'll get right into an example here. Okay, but if we did want the current itself, of course, since current is J times A here, if we want the current, we can of course write that the current in a wire would be N E charge density, sorry, density of charge carriers times their charge, E, times that drift velocity, then multiply by the cross-sectional area of that wire there. Okay, so there's our little review of current density. Let's go ahead and get into an example now. So I will go ahead, well, let me leave this here. I'll go ahead and grab an example from the book, and then what we'll do is we'll go ahead and beef the example up if we need to cover a little bit more, or if we have any particular questions, like what would we do if this was different, that kind of thing. Okay, so I have a problem here. I think that's enough time for you guys to copy that down, so we'll go ahead and go down here. So this will be our example one. And you might remember this. This is going to be a similar example to one we've done in the past, but I'll change it up. I'll change the numbers and stuff, and we'll ask slightly different questions about it. So we're looking at a wire with a diameter of 2.00 millimeters. Okay. The wire carries a current, and we'll go ahead and go with 300 milliamps here for the current. Okay. And this wire is powering a 40-watt bulb. Okay. And the wire has a density of free charge carriers of 8.5 times 10 to the 28 inverse cubic meters. Part A here, we want to find the current density. Part B, we want to find the drift velocity. Okay. And then let's go ahead and add in a little bit more, because this is only, this is a small example here. Let's go ahead and add in some more questions, some other questions that we might be able to ask here. Maybe you guys can even think of some things that you could ask yourselves. Might be something like, what is the resistance of the bulb? Right? We know a little bit more about circuits and things now. And so now we could ask this question, a couple of chapters ago. You could ask, what's the resistance in the bulb here? We could even ask something along the lines of, if I say that the length of the wire, well, actually, let's go ahead and put this up here. Let's say length of the wire is, let's just keep it simple. It's 1 meter long wire. Okay, then we could come over here and we could say, okay, what's the resistance of the wire? Right? Well, we have current, we have resistors, right? We could also ask, what's the EMF, right? So you see, now that we've got a little bit more tools under our belt, we can always go back and revisit older material, from previous chapters, and kind of take a look at those same example problems again and kind of ask a few more things. That's a really good way to get some new practice for the different topics that we're covering throughout the class. Okay, let's go ahead and stop it there, 5 parts. Okay, so the way we've been doing this, and I think it's good for you guys, is on the first one, I kind of work through it a little bit slow. And then on the next, and then you guys kind of follow along. And then on the next couple examples, I just kind of let you guys work on them, on your own or whatever you want to do. If you guys want to do breakout rooms, let me know. We can do it that way too. Okay, so do we want to do that? Do we want to see me work through maybe parts A and B, and then maybe you guys can work on C, D, and E? What do we think about that? Just give me a thumbs up if that's good, or maybe say something in the chat if you guys just want to work on this one by yourselves, or do you guys want to see me do this one or some of it? Okay, so let me just go ahead and cover the first part here. I'll go through A and B. So as we just kind of reviewed, current density. My mouse is giving me a little bit of trouble again. Current density is the density of free charge carriers times the charge of those charge carriers times the drift velocity. Okay, let's take a look at this formula here, because I noticed something immediately. I'm being asked to calculate the current density, but wait a minute, I'm also being asked to calculate the drift velocity. So some of you have probably been in this situation before. You're thinking about a formula. There's a formula right there for the current density, but we don't have enough information to use that formula. So you have to remember another formula. You have to remember, okay, we can't use this one. Try to keep things colorful here. We have to use this formula. The current density is the current per unit cross-sectional area of the wire. Okay. So let's go ahead and highlight the information that we need here. Maybe I'll do this. Yeah, let's go ahead and keep that the same color here. So we'll go red here. We need this information right here, the diameter of the wire, right, to calculate its cross-sectional area. And then of course we need this right here, the amount of current that flows in the wire, okay? So we can go ahead and convert those into units that we need here. So 0.300 amps. Okay, so that's milliamps to amps, right? Times 10 to the minus third for milli. Move the decimal place over to the left 3 times. And then we're given the diameter of the wire, 2 millimeters. It's a pretty thick wire, to be honest. How do we get the cross-sectional area of a wire when we're given the diameter? Well, we can divide the diameter by 2 and then do pi times r squared, right? Or we can use the formula for the area with the diameter in it, which is pi. Well, let's go ahead and just write it up here. So the area, when you're given the diameter, is pi d squared over 4, right? Because you got to divide the diameter by 2, get the radius. So it's pi over 4, and then the diameter there is 0.002 meters, and we want to square that. Okay. Now, one thing I noticed, I actually was grading labs, and I believe it was the 6:10 p.m. class, I think. Some students were making small conversion errors. So just double check, when you're going to convert something, just double check that it makes sense, okay? So I think the mistake was converting centimeters to meters. So it's 10 to the minus 2 centimeters per meter, or excuse me, 10 to the minus 2 meters per centimeter, and it's 10 to the minus 3 meters per millimeter, okay? So just make sure you got that correct. So this is a matter of just plugging into the calculator now, right? So let's try and be efficient with our time. I'm just going to go ahead and do this myself here. You can follow along with your calculator if you want to. So 0.300 divided by, and I got to do pi over 4, and then times 0.002, and I want to square that 0.002, and I make sure I've got my parentheses in the correct location there. I push enter. I double check that the expression looks correct as I plugged it in, and I get an answer here. And we'll go ahead and write this down in scientific notation here. I get 95.4 times 10 to the third amps per meter squared. You could write that as kiloamps per meter squared as well, right? So we could write kiloamps. If you want to, feel free to do that. So that's the current density there. That's a pretty straightforward application of just the definition of the current density there, which is current per unit area. Okay, now how about the drift velocity? Well, now it looks like since I've calculated the current density, I can go back and look at that formula I wrote down initially to calculate the current density, right? So let me go ahead and clean it up here. So this formula right here, I'm going to rewrite it now. Turned out we needed to use this formula to get the current density, but now we can use, let's go ahead and not solve for it just yet. We can use this formula here to get the drift velocity, right? So we'll solve this for the drift velocity. I'll go ahead and do that here. Drift velocity is current density divided by the free density of charge carriers. Excuse me, the density of free charge carriers times their charge, which is going to be E. And we're already just ready to plug everything in, right? So usually getting started on the problem is usually the hardest part, right? So got to look at kind of reason things out. And then once you get a start, then things start to fall into place here. So 95.4 times 10 to the third. I'm gonna go ahead and leave the units off for a second. Let's go ahead and get a little divider here. So 95.4 times 10 to the third, that's the current density there. And then the density of free charge carriers is this information here. So 8.5 times, mouse is giving me some trouble here. 8.5 times 10 to the 28. And then we also need to divide by the charge, 1.6 times 10 to the minus 19. And I see we have a question, so go ahead.
For the E, I believe, or no, N, is it the same number? Is that the constant, or is that going to be given?
So the N is like a density. It's like the number of charges that you have available to move freely in the circuit. So if you think about a material like copper, copper is going to have some number of electrons that are free to move around. That's kind of given by the certain number of electrons in that atom, which are in what's called a conduction band. Like their orbitals are in this certain range of energy levels, which allows them to kind of freely move around. But like a metal like tungsten, for example, it has different properties. It's a different atom, right? And so for that specific atom, then there's a different number of electrons that will be available in that conduction band region. So it really depends on the material that you're looking at. I believe like one kind of example I could just throw out off the top of my head is copper has of the order of 10 to the 28 per cubic meter, whereas silicon, around like room temperature, has something like 10 to the 19 or 10 to the 20. So it's got a lot less free electrons. So different material, different value of N. Does that make sense?
But we're mainly going to be dealing with copper, right?
Well, whatever material that I put on there, I'll give you the value. I'm not gonna like expect you to have it memorized.
Okay.
So like
Thank
if I say silver and I'll just give you the value for silver.
you. Okay.
Did that answer kind of what the meaning is though?
Yeah.
Okay. All right. So just to finish off this calculation now, so go ahead and do it yourselves if you're following along here. So 95.4 times 10 to the third divided by 8.5 times 10 to the 28. Notice we're dividing by a very large number, this 10 to the 28 roughly, right? And that is because drift velocity, like I said, it's always very small compared to the random motion of the charges. The random motion of charges in a material, the electrons around their atoms, is of the order 10 to the 6 meters per second. The order of the drift velocity is usually on the order of like millimeters per second, maybe centimeters per second, depends on how much current you have flowing, how big the EMF source is and things like that. So when I calculate this here, I see actually, yes, indeed a very small number here. And this one is on the order of 10 to the minus 6. So 7.01 times 10 to the minus 6 meters per second. So this one is even smaller. The reason it's even smaller is we have a very small current in a very large wire. The wire has 2 millimeters diameter, which is very big for a wire. And then 300 milliamps is a very small amount of current for such a large wire. And so that's why we've got this like micrometers per second drift velocity. It's a very small drift velocity. So always try to think about that. Try to think about the physical dimensions of what you have, right? What is actually going on in the problem with a small current for a big wire, and the material is, some very conductive material here, so small drift velocities. Any other questions about those first two parts there? I want to let you guys work on C, D, and E. But let me give you guys some hints before I do that. And can we just get a quick vote in the chat? Can you guys just say a 1 in the chat? So let me write it out. 1 in chat for work alone, 2 in chat for breakout rooms. So I'll let you guys choose. It looks like an overwhelming number of of ones. Okay, so I'll let you guys work alone on this one, and then maybe on the next one I'll do breakout rooms for you guys. We are coming up on the test, so maybe it is best if we all work on our own mostly, just to simulate more of like a test environment. But let me give you guys a quick hint here on these next couple. So we need to remember that for a bulb, well, number one, the resistance of a bulb changes, right? As the bulb heats up and it turns on, right? Its resistance goes up as a function of temperature. Not something we're going to be tested on, but just a fact, right? So what's the best way to calculate the resistance of the bulb here? Well, I know it's a 40-watt bulb. Units of watts because it's power, right? Well, 40 watts is a power. And power for a resistor, I can always write down as I squared times R, okay? So there you go. You can write down I squared times R for this bulb. How about the resistance in the wire? Another topic we need to do a quick review on resistance in a wire. Recall that if I have a wire, it's a cylindrically symmetric object. And so a wire looks something like this. It has a length, it has a cross-sectional area, and it's made up of some material. And that material has a resistivity rho. Okay. And I'll just for the sake of being complete here, I need to give you a value for resistivity here. Let's go ahead and just take let's just go ahead and take the resistivity to be, let's just say 2 times 10 to the minus 8 ohm meters. Okay. So use that value of the resistivity there. The resistance of this wire, it's not super obvious, but remember how we came up with it? We started with an expression like the electric field is proportional to the current density, and the constant proportionality we call the conductivity, or 1 over the resistivity. And then we assumed we had a constant potential, or excuse me, we had a constant electric field, and so we had a constant current density. And then we looked at the dimensions of things, and we replaced the electric field with a potential difference times the length, and we replaced the current density with a current times the area, and we came up with this expression for the resistance of a wire. The resistance of a wire depends on the resistivity of the wire times its length. The longer the wire, the more resistance, divided by its cross-sectional area. The thicker the wire, the lower its resistance. Okay, those are like the things that you remember to help you remember the formula. Longer wire, more resistance. Thicker wire, less resistance. Okay, so we want to get the resistance of the wire there as rho times L over A. I'll let you guys figure this part out, okay? I'll let you guys figure out how to calculate the EMF there. Just make sure that you set yourself up a little circuit, right? And then calculate what the EMF would be. Okay, so I'm going to go ahead and let you guys work now. So I'll give you guys, let's say 10 minutes here. Okay, I'll give you guys 10 minutes. If you happen to finish earlier than 10 minutes, then you get a little bit of break time. Okay, it should take maybe about 5 minutes, I would say, to finish these three parts. So we've got a 5 minute break time kind of worked in here, and that's how we'll kind of do it. I know maybe not everyone was here for the review session on Saturday. That's kind of how we were doing it. It seemed to be working pretty good. So we're working in a little bit of break time here and there. So I'm going to turn off my video and mute my microphone, but I'll still be here. So if somebody direct messages me a question or something, I can still answer that. Um, when you calculate your answers for part C, right, put the answer in the chat so other people can compare their answers. Do the same for D, do the same for E, okay? As you get an answer, put it in the chat so everyone knows. And then they can see, okay, who made a mistake? Did anybody make a mistake, right? And you can compare your answers. Okay, so that's the plan. Thumbs up if we're ready to start. Okay. All right, so let's go ahead and get started. I'll give you guys 10 minutes. I'll be around, so just direct message me in the chat if you have a question or something like that, and I'll get around to it. Okay, I see pretty much everybody getting the correct answers here for the questions. Does anybody have any questions about how to go through those? Were there any difficulties? Okay, give me a thumbs up if we're all here and we're ready to move on to the next topic. Okay. Good majority. Okay, so let's go ahead and move on then. So we'll scroll up here and recall the next topics we want to go into are resistivity, and that's kind of the same kind of topic here as resistance of a wire. And we kind of already added that into this problem, but let's go ahead and do a problem a little bit more specific to that. Maybe we can integrate some additional questions. Let me go ahead and pull this one up that I have here. Okay, here it is. I'll try and change the colors up a little bit so we don't get too bored. So we'll go ahead and take a look at a wire with a diameter, or rather a cross-sectional area of 10.2 times 10 to the minus 7 meters squared. Carries a current, should be a comma there, carries a current of 3.10 amps. So this is the setup here. This is all we need. And then we'll go ahead and we'll calculate some stuff here. What is the electric field? Well, I probably have to tell you it's a copper wire actually. What is the electric field? And I'll write down the information for copper here in a second. What is the electric field in the wire? What is the potential difference and they want the potential difference specifically between points on the wire which are a length of 50 meters apart, and then the resistance of that wire, again for the 50 meters. Let me get you the more information on copper here. So resistivity for copper, 2.4. I forget what it is. Let me just grab the exact value here, or the value from the book, I mean. Oh no, 1.72. 1.72, 2.4, that's gold. 1.72 times 10 to the minus 8 ohm meters. And that is all we need to do this problem. We have a cross section of area, we have a current, we have the resistivity of the material. We can calculate the electric field, we can calculate delta V, we can calculate R. Now let's go ahead and add in a problem to this, and actually it's something we have to do already anyways to calculate part A. We actually have to get the current density in order to calculate part A here. So let's add in to part A, what's the current density, right? This makes sense. Another thing we could do, of course, if we can get the current density, we can also get the drift velocity, right? Let's go ahead and add in the drift velocity here. My mouse is really not wanting to work today, huh? So add in the drift velocity there. Again, we can think about something like power, right? We can think about power dissipated by the resistor, right? Can anybody think of anything else that we can ask about this particular wire here that maybe we don't have written on the board already? Anybody have any ideas? Okay, well, if nobody has anything that they want to add, this is pretty comprehensive here, I would say. So again, let's do it exactly the same way. So try to do 10 minutes a problem. If we come across a problem that takes a little bit longer, actually we did last time, we came across a problem, took a little bit longer than expected, but we just gave a little bit more time, broke it down into parts. Let's go ahead and give 10 minutes again. Okay, and I'll be around. So ask questions if you have questions. If you finish early, you get a little bit extra break time. If you finish early, think about what I just asked. Like, is there anything else we might want to know about this system here? Like, is there anything else that we can calculate? Um, yeah, think about that, and then maybe you'll have something. Okay, so another 10-minute problem here, broken down into small parts. So go ahead and get started on that. I'll go ahead and mute and turn off the video again and just let you guys focus. Oh, actually, you know what? I did say we would do breakout rooms on this one, didn't I? So actually, we will do that. I'll go ahead and put you guys in breakout rooms now. We'll do 7 rooms, two people per room. Okay, so 10 minutes. We'll meet back at 7:20. Go ahead and join your rooms. Elaine, Sergio. Elaine, are you there? Hey, Elaine doesn't seem to be here at the moment. Are you okay working by yourself, or do you want me to put you in another group?
I'm okay.
Okay, I'll just leave you here then. Give some time for some people to come back. Was that enough time for you guys to finish off the problem? Okay, good. Okay, looks like everybody's kind of back in here now. Okay, so I've kind of written down, so I'll just kind of run you guys through this. I've kind of written down, like how you would calculate this stuff here, current density, electric field. For the drift velocity, I didn't mention this, but I think maybe since a lot of you figured out, finished the problem, that you're supposed to use that 8.5 times 10 to the 28 number for n if you want to calculate the drift velocity. 8.5 times 10. Were you guys able to figure that out? 10 to the 28 inverse cubic meters. Okay, that's good. And then also on bottom is the 1.6 times 10 to the minus 19 here, and so forth. So let me know if there are any questions with regards to how to do this question here. I'm just gonna run through the various ideas here. Of how to calculate, but maybe I don't have to calculate everything exactly since you guys already got your answers to the questions. Why don't you guys go ahead and punch in the chat your answers that you had for all of the parts. That way everyone is on the same page. We can all see, we can all compare our answers. So go ahead and do that right now. So type your answers for each of the parts into the chat. Now that everybody's in the same room, we can all see each other's answers. Do we have answers? Are we just typing them? Okay, got some answers finally. Anyone else? Are we still typing? I know it's a lot of numbers to punch in here, but Here we go, getting some more answers now. Okay, looks like we're pretty much in agreement for the most part. Maybe 8.07 watts, 8.01 watts here. It's probably just a little rounding, no big deal. Yeah, looks like you guys are doing everything correctly. These are the answers that I kind of was getting over here on the side. I was kind of writing them out. And just looking at some simple stuff here, like for delta V, the electric field is roughly 52 millinewtons per coulomb. I'm going to multiply that thing by 50 meters, right? So it's like 50 times 50, right? And then I just got to move the decimal place over. So that voltage looks good. This is a pretty thick wire, and it's a copper wire, so less than 1 ohm resistance seems pretty natural. Even though it's pretty long, it's also pretty thick. Current squared times the resistance, yeah, seems to come out to around 8. Current squared is about 9. Resistance about 0.8. So it looks good. Okay, so I'm glad everybody's getting these answers. So let's go ahead and then just move on to the next question then. Yeah, give me a thumbs up if you want to move on to the next one. Use the hand if you have a question about something. Okay, and in case you didn't see the message that I broadcast earlier, I put up a practice, a test 2 practice. I selected problems on Mastering Physics that Mastering Physics tells me take roughly, like 6-7 minutes or less. So I put some conceptual questions from each chapter on there, and I put just a bunch of different problems on there. It's a lot of questions overall, but remember, they're all practice. They're worth 0 points. Okay, so don't feel pressure to go through every single question. The questions are also ordered. So it's chapter 24, then it's chapter 25, then it's chapter 26. Okay, so if you need more practice in chapter 25, you have to open up that assignment and kind of go to the chapter 25 questions. Okay. All right, so let's go ahead and get another problem going here. We've been doing a lot of work in this last section with capacitors and resistors, and I noticed some students have been mixing up the formulas a little bit, and so maybe it's a good idea for us to take a look at a couple setups with some resistors here, maybe. So let's go ahead and draw out some circuits. Go. Let me make sure I stop clicking every so often. Okay, so if I have a setup like this, let's go ahead and add some numbers in here. 10 ohms, 5 ohms, make this one 3 ohms. Don't want to give you guys too nice of numbers. Let's throw in an odd 3 ohms in there. Make this one 7 ohms. 4 ohms here. 2 ohms. 3 ohms, and 11 ohms. Okay, what is Req for this circuit? And then after this, we'll go ahead and do a CEQ type of problem. Let's go ahead and write down on the side over here. These are the things that you would be expected to know for the exam. So like parallel elements, they share the same voltage. You guys can read this, right? Okay, let me just write it out. I'll just type it out so it's a little bit quicker.
Someone is trying to summon Cthulhu.
Okay. Oh, I can't even move this text box. Okay, let's try it. There we go. Okay. Parallel elements share the same voltage. Series elements share the same current. Okay, so just a reminder for you guys, that those two statements right there can help you remember what rules to use for parallel and series capacitors and resistors. So if two elements share the same voltage, then what you do is you solve their respective equation for the voltage, and then you should immediately understand which formula to use. So if you have Q equals CV, if I solve this formula for voltage, or wait a minute, no, sorry. Let's start with this formula here. So if I have two elements in series, then, or sorry, I said parallel first, right? So if I have two elements in parallel, then they share the same voltage, okay? So I start by writing down the equation that's characteristic for whatever element I'm working on. So if I'm working on resistors, okay, voltage is current times resistance. Now, if they share the same voltage, then that means that this stays the same here. V stays the same. But the currents have to split. Okay, so it has to be one current going on one resistor and one current going on the other resistor. So the sum of the two currents has to give you the total current, okay? But the voltage stays the same. So it's the sum of the currents. So what it is it's I1 plus I2 is equal to the total current. Maybe let's put current like IEQ. It's not something I've written down before, but what I mean is the current that would be flowing through the equivalent source. Okay. So since they share the same voltage, it's the sum of the currents. So if I were to sum these two currents here, then I'd have to write the current as V over R, and it would be an R1, and I'd have to write a V over R2, and then for IEQ, it would be the same voltage again, because we're working with stuff in parallel here, so all the voltages are the same, and then V over REQ for IEQ there. So I know the voltage is the same for those elements in parallel. And since the voltage is the same, then it's the current that splits into two parts. Well, it's in parallel, right? That makes sense. So if they're in parallel, the current's going to split into two parts. And so I have to add up the two currents. Then you just replace them with V over R, V over R, V over R. And it's like, boom, you see it right there, right? The voltages cancel. All the voltages cancel here, right? And you have the formula right there. You can do the same thing with series as well. Let me see, I see some chats here. Can you tell us what the resistance in the middle resistor is? It's a 7 ohms. Okay, so if you want to look at resistors in series, well, in series they don't have the same voltage, they have the same current, right? So write it down like this. Or, well, you can just look at it right here. If they have the same current, that means they have different voltages. So it means that you have V1, which is the voltage across the element R1, plus V2 has to be equal to, and I'll call it VEQ. Okay. Just replace V1 with I times R1. So I times R1 plus I times R2. And that's got to be I times REQ. And then boom, you can already see what formula you're supposed to use, right? So for series, they share the same current. For parallel, they share the same voltage. Okay. There's your tricks right there. How does it work for capacitors? I'll let you figure out how it works for capacitors, but it's the same thing. For capacitors in parallel, they share the same voltage, so their charges are different, right? So Q1 plus Q2 equals QEQ. And you just replace all those Q's with C times V. For series capacitors, they share the same charge and they have different voltages. So it's the sum of the voltages. So V1 plus V2 equals VEQ. And then, so replace the V's with Q over C. And then you already can see it. Okay, it's going to be 1 over C plus 1 over C. That type of thing. So how are we doing on this one? I know some people already have the answer here, but how's everybody else doing on this one? Anybody have any questions? Anybody stuck anywhere? Okay, so it seems people just working. That's good. It's a 5, yeah. It's a 5. Talking about this one right here, right? So this is the kind of question here that could show up on the exam, but I would expect you to be able to do this question in, in like less than 5 minutes, but it's already been a little bit over 5 minutes. So um, I'm just wondering what's the, like what's the part that slows you guys down the most? If you could let me know, then I can maybe talk specifically about that. I'm going to go ahead and start writing some stuff down here in the bottom left corner because I have some space. Hopefully that will maybe help you guys out a little bit. Okay, I'll talk about that specifically in a second. So when I first look at the circuit here, I'm looking at these 3 resistors on the left here, and I'm recognizing that all 3 of them are in parallel. So that's not too bad. The 3 resistors all on the left are in parallel. Of course, whatever I get for my REQ for this little parallel combo right here is going to be in series with this 7 ohm resistor right here. So whatever I calculate for the 3 in parallel, I would just add 7 to that. And then I'm looking at the right hand side over here and this little diamond shape. Don't let the diamond shape fool you here. You can easily redraw this diamond shape. And I'll go ahead and do this actually in the bottom left here. This diamond shape is simply 2 resistors in series with 2 other resistors. Or sorry, 2 resistors in series in parallel with 2 other resistors. So this diamond shape right here you could redraw. You could redraw and make it look like this. And so you could just add the 4 and the 2, you can add the 3 and the 11, and then calculate the parallel combo for that. Okay, so I'm only going to give you guys another 60 seconds on this one. And then I guess what I'll do is I'll go through the problem quickly so that way you guys can see. Because you do need to be a little bit quick on these kind of problems here because they come up a lot in this. They're going to come up in the future in this class as well, like in later chapters. So we're always going to be talking about circuits from here on out. So we're going to talk about magnetic components of circuits called inductors, and then we're going to talk about AC circuits and things. So you really want to be comfortable with a lot of this circuit stuff. Plus, a lot of you are probably engineering majors and you're going to eventually take a circuits class, and you're really going to want to be good at this stuff so you don't have to learn it while you're in that class. So very important, this stuff. Okay, so I'm going to go ahead and go through the calculations on this now. So a 10, a 5, and a 3 in parallel. Well, I have 3, so let's do 1 over 10 plus 1 over 5 plus 1 over 3. That's 1 over REQ for just that little parallel piece there. I can make these a 15 if I put a 5 on top. I can make this a 15 if I put a 3 on top. Right, and so 1 plus 3 plus 5 is 9 over 15. So 1 over REQ equals 9 over 15. That means REQ equals 15 over 9. That's just for the left side of the circuit. Okay. Let's try to get this thing to work. There we go. That's better. So, oh yeah, I did mess that up, didn't I? What am I doing here? Oh, so 6, and then this one is 10. Oops, my bad. And a 3. So 9, 19 over 30. My bad. 19 over 30. So REQ is 30 over 19. Okay. And once we have this, what is that REQ? That's just these 3 resistors in parallel right here. So maybe I'll use another color. So these 3 in parallel right here. So I just need to add in now the 7 ohms. So we can take this, we can add in 7 ohms. Okay, so that's 143 or something like that. 19ths. Let's just maybe go with decimal answers here. You guys tell me what to write here for this. Okay, once I add in 7, let me go ahead now and work on these two. These two are a 6 ohm resistor. Those guys are in series there. Okay, and we have an 11 and a 3 here. That's 14. So a 6 and a 14 in parallel is 6 times 14 divided by 6 plus 14. So 6 times 14 divided by 20. Okay, 163 over 19 for this answer here. That's an exact answer. And then we're going to add into that 84 over 20. Well, what do we get for that? 21 over 5? Oh no, that's this right here, right? Oh my goodness, my mouse just doesn't want to work. Okay. So I got to add up those two now, and then what are you going to get in the end? Something like 8 plus 4, roughly 12 for your answer. So just approximating here, the answer is going to be roughly 12 ohms. Let me walk through that one more time just to make sure we're clear exactly what's going on here. Okay. What's the approximate answer? What's the decimal answer, Sean? Do you have it? Just calculate it real quick. I can go ahead and just punch it in myself here. It's over 95. So the answer is like 12. So 12 point roughly 8 ohms. Okay, thank you. So roughly 12.8 ohms there, or 7.8, yeah, that works too. So there's our answer for REQ here, but what's the process? Let's go through the process again. We have 3 in parallel here. Let's do this. 3 in parallel. Okay, that's going to be in series. And then here we have 2 in parallel. Oh, sorry. Excuse me. It's 2 in series with in parallel. In parallel with 2 in series. Okay. Oh, that erases the text too, apparently. Okay, let's move it. 2 in series, in parallel with 2 in series. See if I can move this. There we go. Okay, so that's the process there. So identifying all that is the first step. This particular circuit is actually not difficult. The reason it's not difficult is because I can reduce the circuit in any way that I want. That is not always true. There are a lot of circuits where you have to reduce the circuit in a certain way because it's impossible to reduce the circuit another way. So this is as an example of a circuit which I would consider an easy circuit problem or REQ problem because I can choose to go about this in any way that I want. I can do from the left first, I can do from the right first. The only thing I can't do is I can't really do anything from the middle first. But yeah, so there you go. That's the process. You have 3 in parallel on the right. That's going to be in series with that one in the middle. And then those 2 are going to be in series with the 4 all the way on the right side. But you got to make sure you combine those in the right way. So it's 2 in series, and the other 2 are in series, and then those 2 combos are in parallel. Okay, so let's do now a capacitor problem. Oops. Okay, and let's go ahead and give some values here. I'm going to give the values with no units, okay? Just assume all the capacitors have units of microfarads or something, it won't matter. I'm just going to give numbers here because we're really just interested in practicing how to combine these things. So I'll go 10, 5, 1, 8, 9, make this one a 7, this one can be a 6, this one can be a 4. Let's go ahead and add in a 3 and a 2. Here's a 3, here's a 2. No integers less than 10. No natural numbers less than 10 left behind, okay? So there you go. Go ahead, I'll give you guys 10 minutes on this one. And any additional time you can have as a break. I will again, I'll mute and turn off my video, but I'll still be here. If you have a question, you can just ask. Okay. Do we want to do breakout rooms for this one? Just before I release you guys, do we want to do breakout rooms for this one? If that would make things go faster, then that's probably a good idea, because you want to build a little bit of speed for these kind of questions, right? So have a little bit of speed so you have extra time on the exam. Do we want to do breakout rooms? Well, if you're not drawing the circuit into your notes, you're probably not studying effectively. You probably should be redrawing the circuit and writing all of your steps out by hand. That will help you remember what you've done. So if you're not doing that, I do recommend that you do that. Write everything down, every problem that we go over. We'll go ahead and we won't do breakout rooms on this one, but maybe on the next one we'll do breakout rooms, okay? So 10 minutes, we'll meet back at 8:10. Okay, it seems like there's a lot of people in agreement here in the chat. Let me know if you are not getting what others are getting in the chat. Okay, let me remind everyone of the rules here. So for capacitors in parallel, CEQ is C1 plus C2. Wow, my mouse is just magically working now. For series, you can do CEQ as C1, C2 over C1 plus C2. Or if you have many capacitors in series, oh, there we go, now it's giving in. It's going to be the sum of the reciprocals. So 1 over C1 plus 1 over C2 plus 1 over C3 and so on. Okay. So all the way on the right side of this circuit is where we have to start in this problem. We cannot start on the left side of the circuit. There's maybe only one combination we could do on the left side of the circuit. Only one. And that would be that these two elements here are in parallel. There are no other combinations that we can start with except all the way on the right side. So we have to start here with the 3 and the 2 here. So a 3 and a 2 in series is 6 over 5, product over sum. So this is 6 over 5. There we go, it's not working now. So 6 over 5 for that one. Well, then we have 6 over 5 plus 8. So I'm going to add in 8. Now we have to combine these two with this one. So Sean tells us 46 over 5. So we're going to do 1 over 46 over 5 plus 1 over 1 and plus 1 over 9. So we're just adding up these capacitors reciprocals because they're in series here. The purple circle here is 3 capacitors in series, right? We have this green equivalent capacitor, which is these 3 here. That one is in series with the 1, and it's in series with the 9 there. So that's 1 over CEQ. I'm just going to default to the calculator on this because we don't want to spend a bunch of time calculating all this out. So it's 5 over 46 plus 1 plus 1 over 9. And then I want to invert that expression. So I'll put it to the power -1. And what I end up with for that is 0.81 or 0.82. So 0.82 here. And you got to ask yourself at this point, does this answer make sense? When you have capacitors in series, you always end up with less capacitance than any of the capacitors in series. So 0.820 is less than 1. So that's our check right there. 0.82 is less than 1, so we're good. All right, well, now we have the purple in parallel with the pink here. So purple in parallel with pink. So we're going to add in 7. We add in 7 to this guy, we get 7.820. Excuse me. Now that we have 7 for the pink loop here, the next thing we have to do is we got to be really careful now. We have to be really careful. We can only combine the pink with the 5 here. We have to combine the pink with the 5 first. Don't make the mistake of trying to combine the pink, the 5, the 6, and the 4 all at the same time. That would not work. That would be incorrect. We have to combine the 5 with the pink. So that would be 5 times this. They're in series, by the way. The 5 and the 7.82 are in series. So that would be 5 times 7.82 divided by 5 plus 7.82. I'll just run that in the calculator over here real quick. 5 times 7.82 divided by parentheses. Now it's just going to be 12.82. So comes out to 3.05. So 3.05. Okay. So the 5 in combo with the pink here is 3.05. Does that check out? Yes, it does, because 3 is less than 5 and it's less than the 7.8. So that checks out. At least, conceptually, that checks out. All right, so now we have the brown capacitor, the brown equivalent capacitor, and that capacitor indeed is in parallel with these other 2 capacitors here. So the 4 and the 6, they are definitely in parallel. So we can combine those 3 all at once. We can do 1 over 3.05 plus 1 over 6 plus 1 over 4. And in the calculator, I plug it in like this. I put it to the -1 power. Go ahead and do that. So 1 over 3.05 plus 1 over 6 plus 1 over 4. Raise that to the -1 power, and we get 1.34.
Also, they're in parallel.
Oh, I've made a huge mistake. I've made a huge mistake. Thank you for pointing that out. That is incorrect. They are in parallel indeed, so we should add them. That should be 3.05 plus 6 plus 4. That was a good catch there. Going a little bit too fast. So that is 13.05. Okay, so 13.05. Everybody can make mistakes, right? Okay, now we have 13.05. That is going to be in parallel with the 10 right there. So we'll do that one in orange, I guess. Now this one is a series, so this one will be sum of the reciprocals or product over sum. Let's go ahead and do product over sum. So 10 times 13.05 over 23.05, so 10 plus 13.05. And this one comes out to 10 times 13.05 divided by 23.05, 5.66, which is the answer that a lot of you were getting earlier, so that is a very good sign. Okay, so are there any questions about that one? Any questions about that one there? Give me a thumbs up if you are ready to move on to the next problem. Okay. All right, cool. Let's go ahead and go to the next one then. And the next one, our last topic is going to be RC circuits. I will go ahead and grab a problem here. I have to log back in for some reason. Last time we looked at RC circuits, we kind of took a resistive circuit piece and a capacitive circuit piece and kind of combined them and then reduced them down to their equivalent circuits. And then from there, we kind of asked a couple like RC circuit type questions. This time, I'll just go ahead and pull a problem from the book. So that way we can take an established problem and we'll ask a couple extra problems, or we'll ask a couple extra parts that we can kind of have a more complete example. Find RC circuits here. Okay, here we go. Okay, we'll go ahead and take this example here. So let me go ahead and draw the circuit diagram first, and then we'll get to the actually copying down the question portion. And I'm sure you guys have seen on the homework, but I don't always do this. A lot of the questions when capacitors and resistors are involved, they always start with a switch. Usually they label the switch like S or something like that. And they always talk about the initial time. T equals 0 is when the switch is closed and things like that. That kind of information is necessary for setting up the differential equation for solving these kind of problems. But from our kind of physics standpoint, we kind of understand what's going on. We don't always need to be exact mathematically all the time once we kind of know what's going on. This capacitor will begin with an initial amount of charge Q0 here. And then last we have these points A, B, and C. Okay, let's go ahead and now get the question. I'll just go ahead and type up the question here. So go ahead and give myself some space here. So the capacitor has an initial charge, Q0, or well, Q equals, yeah, I guess I kind of have to put, let's do it that way maybe, 5.0 microcoulombs, and is discharged by closing the switch at T equals 0. Part A, at what time will the charge be 0.50 microcoulombs? And B, what is the current at this time? Okay, so here's part A. Let's maybe throw another color on it. And then part B. Okay, so there is the question. Now, for these RC circuit problems, they're a little bit just kind of like setting them up and remembering the exponential formulas and stuff. Remember I told you guys um, the most important thing you can do when solving RC circuit problems is to have the following two functions memorized, okay? These are just mathematical functions, and you want to have them memorized, although actually on a test I will give you these functions, but it just really, really helps if you have these functions memorized. Just purely mathematical. E to the minus t over tau is one of them, and the other one is 1 minus e to the minus t over tau. Okay, if you have these two functions memorized, you can literally figure out all of the stuff in an RC circuit like very quickly, like all of the functions of time, the voltages, the current, the charge on the capacitor. And then of course, if you know them as a function of time, you can figure them out at any point in time as well, right? So knowing these two functions here helps big time when doing these problems. Okay, and I'll let you figure out how these functions look, which one starts at a maximum and decreases to zero, which one starts at zero and increases to a maximum, right? So you figure that out. I'll go ahead and give you guys, I'll go ahead and give you guys 5 minutes to do these two parts, A and B. And while you guys are doing parts A and B, I will come up with maybe parts C, D, and E for this question. So you guys go ahead and get started on this, and I'll meet back in with you guys in 5 minutes. Nothing that I write on Paint is going to be relevant for parts A and B. So don't get confused. I'm going to start writing stuff here. It's not for you guys. It's for when you're done. Okay. So go ahead and start working on that, and I'll check back in at 8:31. Okay, so it's been 5 minutes, but I noticed nobody's given any answers yet, so I'll go ahead and give another 5 minutes on that. Is that, do you guys think that'd be enough? So you have to remember how to solve, you have to remember how to solve, for t. Write down the function for the charge. It's a discharging capacitor, right? So which one of these two functions here, which one of these two functions is going to be the characteristic of the charge on the capacitor? So it's going to be Q of t equals Q0 times one of those functions there. So times one of those functions. Is the charge decreasing or is the charge increasing for a discharging capacitor? So that's the idea there. So I'll give you guys another 5 minutes. Do you need tau? Yeah, was it not given here? Oh, it wasn't. I didn't give values for R and C. Whoops. Yeah, it is needed. Sorry about that, guys. Sorry about that. Okay, let me get it real quick. Where was this example? Here it is right here. So use tau. So R times C is 10 seconds. So you do need tau. So R times C is 10 seconds here. Yeah, actually, an R value and a C value were not given. Oh, they were given in a previous example. They were given in a previous example. That's what it was. So they weren't given in this example. But R was 10 megaohms and the capacitance was 1 microfarad. So tau is 10. I'll give you guys another 5 minutes there. We'll meet back at 8:39. Okay, I'm back. How is it going here? So I see a lot of people with some answers now. "23 seconds sounds reasonable for sure. What is the current at this time?" So only a couple people have given an answer on that part. So how are we doing on that part? Do we know what to do for part B? Well, always look at these two functions here. That's the point. Always look at these two functions here. What do you think the current is doing? Do you think the current is increasing, or do you think the current is decreasing? In general, the current is always the derivative of the charge. So if you know what the charge is, you take the derivative to get the current. But we can always write the current as some initial current times one of those functions. So is the current going up or is the current going down for a discharging capacitor? Down, good. Always going to be going down because we're running out of charge on the capacitor. So for part A, we want to solve. I'm just going to give the function here. So the charge as a function of time is going to be some initial amount of charge times e to the minus t over tau. This is the function that is decreasing over time. 1 minus e to the minus t over tau that is an increasing function. And so if we want to solve this thing for a time when the charge is half a microcoulomb, that means we plug in half a microcoulomb on this side, and that's got to be equal to the initial charge, times the exponential. And then you can go about solving this thing. Divide the initial charge over, right? The problem is set up so that that ratio is going to be 1/10 e to the minus t over tau. And then you just go about solving for t there. So take a natural log on both sides, that kind of thing. Pretty straightforward. For part B, once you've found that time, well, then you take that time and you plug it into your function for the current. What was everyone getting for that time again? 23 seconds. So let's just assume that is the correct time there. 23 seconds. Sounds right. If tau is 10 seconds, yeah, about two time constants, the net charge on the capacitor will be about 1/10. That sounds about right. I don't remember the exact values for the time constant. I believe one time constant is like 37%. Two time constants is roughly 90%. Three time constants is like 95, and then 4 time constants like 99, something like that. You can calculate those out if you want to, but they're not really essential. But okay, so we have that t is 23 seconds. We're going to take that and plug that into the following. We want to know what the current is at 23 seconds. Let's just put I of t for now. I of t is I0. The current is decreasing, right? This circuit is eventually going to die off because we don't have a source of EMF, right? We don't have a source of a potential difference in the circuit. We just have the capacitor. So it's I0 e to the minus t over tau for the current. The current is also decreasing. So you just take that 23 seconds, you plug it in over here, and what you're going to find is that you're going to find the value of the current at that time. The question is like, what is I0 though, right? We don't necessarily know what I0 is. Well, I0 is given by Ohm's law. So the potential difference across the resistor is going to be equal to the potential difference across the capacitor. Okay. And on the left-hand side, that is equal to I times R. And on the right-hand side, that is equal to Q over C. And so we can divide R to the other side here. So I0 will end up being Q over RC or Q0 over tau. However you want to solve for it. You could just take a derivative, right, and the answer will pop right out. You'll get this exact answer. Or you can just reason it out, kind of how I did right there, without the use of calculus. All right, so I think that's enough time for those first two parts. So let's go ahead and start up on C, D, and E. C, D, and E here. 3 parts this time. What's the voltage across the resistor at that instant? So at that same value of T, the 23 seconds. How much energy is stored in the capacitor initially? And then how much total energy is dissipated by the resistor? So there's actually a nice way to figure out part E without using any calculus. I'll let you guys kind of think about how you would do that. So let me go ahead and say 10 minutes for this, but if it takes a little bit longer than 10 minutes, that's okay. We can work on it. So another 10 minutes here for these 3 parts. Put your answers in the chat as you get them. How are we gonna, before we start, maybe you guys can write in the chat, how are we gonna get the voltage across the resistor? Oh, my mouse is giving me a lot of trouble here. There we go. Okay, how are we gonna get the voltage across the resistor? You guys tell me in the chat. How do we get the voltage across the resistor? I times R, right? Yeah, Ohm's law, good. How are we gonna get the energy stored in the capacitor initially? So at T equals 0. How are we going to figure out the total energy stored in the capacitor? So somebody else besides Sean or David. How do we get energy stored in a capacitor? Nobody's really answering my question. um, energy equals what for a capacitor? There's 3 different ways we can calculate energy for a capacitor. 3 different ways. There is definitely going to be a question on the test about energy stored in a capacitor. Somebody help us out here. There we go. Right. So, you're missing a factor of 2 though. You're missing a factor of 2 there. Fix it up. Where does the factor of 2 go? There we go. Yep. So, yeah, and also 1/2 Q times V works. So 1/2 Q squared over C, 1/2 Q times V, and there's one other formula. I'll go ahead and fill in that one for you guys. 1/2 CV squared. Those are the 3 formulas you can use to get the energy stored in a capacitor. All right, so how do we calculate how much total energy is dissipated by the resistor? How do we calculate energy dissipated by the resistor? We know that power for a resistor is I squared times R, right? But power is not energy. Power is the rate at which the energy is consumed. Yeah, it's kind of like kinetic energy. Yep, kind of looks similar. Okay, so not quite, guys, not quite. If only it were that easy. It's not that easy. You cannot just multiply by T because the rate at which power is consumed is not constant. The current is an exponential function here of time, and therefore we must integrate. Cannot multiply by T. Remember, power is dE or dW by dt. Wow, my mouse is working so nice right now. Okay, so dE dt is I squared times R. R is a constant, I is not a constant. So you must integrate from 0 to 23 seconds. Okay, I squared. R can just pull right out of the integral, but I squared is a function of t. There is an easier way to do this question, though. There is an easier way to do part E. We do not have to do part E with an integral expression. If we can calculate the total energy stored in the capacitor initially, so the answer for this integral, although we can do this integral, it is not a difficult integral to do. It's the integral of an exponential, right? That's pretty straightforward. If we can calculate the initial energy stored in the capacitor, let's say the initial energy minus the energy at 23 seconds for the capacitor, If the capacitor loses energy, then that energy must have been lost as energy dissipated by the resistor, right? You always have to remember energy conservation. Why do a complicated integral? It's not even really that complicated, right? It's just an exponential. Why do an integral when I can do algebra instead? So here's my algebra. I calculate the energy stored in the capacitor when the charge is 5 microcoulombs, and I calculate the energy stored in the capacitor when the charge is 0.5 microcoulombs, and that will tell me how much energy the resistor had to dissipate. All right, so I'll give you guys 10 minutes. I'm sure a lot of you have kind of already started working on it. So we'll meet back at 9:07 p.m. We can go past 9:20 if we have to, if we really want to get in some extra practice. We are recording. We will post this on YouTube as soon as we can. All right, so I'll meet you guys back here in 10 minutes. Okay, I'm back. How are we doing here on this one? I see a lot of people now with some answers. Do we need some more time on this one? Give me a thumbs up if we need some more time on this one. Okay. All right, so we still have some time, and we can go a little bit past 9:20 if you guys want to. But this is essentially all of the topics that will be on the exam. So we've covered everything in our review sessions now. Now, this particular RC circuit problem here was a discharging capacitor. So obviously the next thing to do might be to take a look again at a charging RC circuit. So where we have an EMF source like this, we have a resistor, we have a capacitor, right? Like so. So we can use the symbol E there, R, and C. And for a circuit like this, let me just go ahead and, pop quiz you guys. Is the charge on the capacitor increasing or decreasing? Let's suppose we have a switch here. Let's go ahead and draw the switch in. Usually these problems have a switch. Okay. Suppose at t equals 0, this is our initial condition, the charge on the capacitor is 0. Okay. Then we close the switch. So write all this down. So at t equals 0, the capacitor has 0 charge on its plates, and we close the switch. Now I want you guys individually, this should only take you 30 seconds, maybe less than, maybe 10 seconds to answer the question I'm about to ask, okay? So this is the setup again. We have an RC circuit here, a series RC circuit. This time we have a voltage source. We have a source of EMF, okay? At t equals 0, the capacitor has 0 charge. I close the switch. What is the function Q of t equal to? Don't put your answers in the chat. What is the function Q of t equal to? The function Q of t. We know that the charge is initially 0, but what is the function that describes the charge over time? This should only take you maximum 30 seconds to answer. Maximum. Give me a thumbs up if you have the answer. Don't put your answer in chat. We have one person with the answer so far. 3 people, 4 people, 5 people, 6, 7, 8. We're missing about 5 people. 4 people. We're missing 4 people. Okay, missing 3 people, I think. 30 seconds is almost up. Okay, I'm going to give the answer now. Since the charge is increasing, it's going to be whatever the maximum charge is, we can figure that out in a second, times 1 minus e to the minus t over tau. Want to take that one step further? What's Q max? Well, Q max is going to be the capacitance of the capacitor times the voltage source, which is E in this case. It's just given in this problem as E instead of delta V. You may have seen the formula with delta V before. Well, in this problem, we were given E, not delta V, so I put E instead. But if you had C times delta V, 1 minus e to the minus t over tau, that is the correct answer. Okay, next pop quiz question. This is going to be also 30 seconds. You should be able to answer this question really in like 10 seconds, but let's go 30 seconds here. What is the potential difference across the resistor as a function of time? 30 seconds. What is the potential difference across the resistor as a function of time? Put a thumbs up if you've got the answer. Okay, about 4 of you have the correct answer. Well, don't necessarily know if it's the correct answer, but we will shortly. A couple more, good. About half of us have the answer. Okay, that's just about everyone. Just about everyone. Okay, the circuit where the capacitor is becoming charged, eventually the capacitor will reach a maximum charge, and then current cannot flow in that part of the circuit anymore. A fully charged capacitor acts like a break in the circuit, an open circuit we call it, and so current will no longer flow. So after a long time, the current in this circuit will go to 0. That means the current begins at a maximum value and ultimately reaches 0 as t goes to infinity. So I would write this as delta V max to start, if my mouse will let me. And then since this is a decreasing function of time, it is going to be e to the minus t over tau. Now, what is delta V max? Well, delta V max, that's the maximum voltage that's going to be on that resistor there. That's going to be E. Pretty straightforward. The maximum voltage in the circuit is going to be E. So E times little e to the minus t over tau, like so. Okay. You could even rewrite this one other way. Maybe you could say it's going to be I max times R e to the minus t over tau. That's also a valid answer there. What would I max be? Well, it would just be delta V over R for the resistor, right? So it'd be E over R. It's the same thing. Okay. One more, and then we'll stop with this question. We'll go to maybe another one. if you guys want to. What is the potential difference across the capacitor as a function of time? Only going to give you 15 seconds this time. Go. 15 seconds. Thumbs up when you're done. Okay, that's 15 seconds. That was most of you. The voltage on the capacitor is increasing with time. So it's going to be E times 1 minus e to the minus t over tau. That's the answer. Okay. That is a charging capacitor in a nutshell there. The only thing that we didn't write down was the current. Let me just go ahead and write that down for you. The current is decreasing as a function of time. So the current as a function of time, you guys can read this, right? Is I max e to the minus t over tau. Let me try and fill in all these gaps here. There's the current. It's decreasing. Okay, decreasing. All right, would you guys like to keep going? Or should we end it there? Should we call it quits there? It's 9:24. We've been a little bit over. We're still recording. We could end it here. We could maybe do a couple more, maybe shorter problems. Don't want to go too long, right? What do you guys want to do? Let me know in the chat. Okay, one person wants to leave. That's fine. Thank you for showing up. Have a safe trip. Some work to do, so can't continue. Okay, it's fine. Okay, let me read through all these real quick. Okay, I'm okay with anything. Am I kind of good with anything? Can you go over the answer for the previous example? Which answer? Oh, for the for C, D, and E. So what is the voltage across the resistor at that instant? So the voltage across the resistor is going to be equal to, by Ohm's law, the current through the resistor times its resistance value. So the resistance value was 10 mega ohms, so 10 to the 6 ohms. And then what was the value of the current? The value of the current was, if we write the current down as a function of time, so the current as a function of time here for this circuit is Q0 over tau e to the minus t over tau. And we want to plug in 23 seconds here for t. Plug in 23 seconds there. So all together, if I wanted to crunch numbers here, let's see, 5 microcoulombs for Q0. So it was 5 times 10 to the minus 6. Tau was 10 seconds, so divide that by 10. And then it would be e to the minus 2.3. So 23 seconds divided by tau, which is 10, so 2.3. That would be the value of the current at 23 seconds. So if you want to crunch that real quick on the calculator, that would be the answer for C. For answer D, how much energy is stored in the capacitor? That's just a matter of, it says initially, by the way, so initially means you use the 5 microcoulombs, so that's just going to be Q squared over 2C. And C is 1 microfarad, as you can see right here. So C is 1 micro. So this comes out to Q is 5 times 10 to the minus 6. We're going to square that. And then we have a 2 in the denominator, and the capacitance is 1 microfarad. So 1 times 10 to the minus 6. It's 1 micro, right? Yeah, 1 micro. So whatever you get for that answer right there. So it looks like it's going to end up being like 2.5 microjoules, because the 10 to the minus 6 is going to cancel with one of them. And then for answer E there, how much total energy is dissipated by the resistor? You can do it the hard way, which is to do this integral, or you can do it the easy way, which is to calculate the difference in energy for the capacitor. So if you want to do the capacitor way, which is the way I'd recommend, you do Q initial squared over 2C minus Q at 23 seconds, which is the 0.5 microcoulombs over 2C. Right, and so you're going to get an answer for that as well, if you want to crunch the numbers on that. So does that help, Alberto? Thank you, Sarah. Yeah, does that help also, Lee? Yeah, thanks. Okay. Okay, cool. All right, so we'll go ahead and end the recording now then, because it seems like, well, let me just go ahead and ask one more time. It seemed like people wanted to stop, but let's go ahead and ask one more time. So 1, if you want to keep going. 1 to keep going, 2 to stop. Okay. We get some more votes here. Okay, I'm guessing some of the other people just don't care if we go or stop. Let's just go ahead and stop it there. We've already kind of gone a bit over. I think this was good. Between the 2 review sessions, like a total of like 6 hours of review, should be pretty good. You guys should be pretty prepared for the exam. So, plus I just added that practice assignment, which I don't think anybody has even looked at yet. That thing has like 30 problems on there. It's like 10 problems or so from each of the chapters if you want some extra practice. Mastering Physics tells me each problem takes about 5 minutes. I did throw in some of the conceptual questions in there too, because I know, right, I'm going to ask some of those on the test. Now, don't expect questions from that assignment to be copied into the exam, right? That's not what I do. But I'll go ahead and end the recording now.